Today, we're taking a pretty epic step-by-step journey into the very geometry of the universe itself. We're going to explore a framework that literally completely redefined our understanding of reality. We'll start with an incredibly simple thought experiment in a falling elevator and scale all the way up to the most extreme cosmic phenomena ever observed. It's a fantastic story of beautiful mathematics and really profound physical intuition. Let's kick things off with this quote from physicist Max Born. He called this theory a remarkable combination of philosophical depth, physical intuition, and mathematical ingenuity. Basically, he admired it as a work of art. And that sets the stage perfectly, because before we even get into the heavy physics, it's just absolutely crucial to appreciate the elegance of Albert Einstein's general theory of relativity. It was born purely out of theoretical necessity, and it totally reshaped the rigid, old-school structure of classical physics. Section 1. The Catalyst, the Equivalence Principle. To understand how we actually got here, I want you to picture Einstein's self-described happiest thought, a person in a free-falling elevator. In that very specific enclosed local environment, they wouldn't feel their own weight. We can break this realization down into two logical steps. First up is the weak equivalence principle. This just means the motion of a body in a gravitational field is totally independent of its mass. In a vacuum, a feather and a hammer drop at the exact same rate. Simple enough, right? But then we elevate this to Einstein's equivalence principle. He proposed that no local experiment can distinguish a freely falling, non-rotating system from a system floating in deep space with zero gravity. Einstein realized that gravity can essentially be locally transformed away just by falling. Well, this leads us to a pretty massive realization. Gravity is not a traditional force. Sorry, Newton. Actually, let's go a step further. It isn't an invisible tether pulling an apple down from a tree at all. If an observer literally cannot tell the difference between zero gravity and free fall, we can't treat gravity as just a pulling mechanism. And that forces us to ask the big question. If it's not a force, what is actually moving the planets and keeping our feet planted on the ground? Section 2. The Revelation, Curving the Fabric of Space. If gravity isn't a pulling force, it has to be a structural feature of the universe itself. Imagine a giant, multidimensional, flexible grid that physically bends around the matter sitting inside it. We formalize this incredible feedback loop with Einstein's field equations. Now, these highly complex mathematical equations are the absolute hardcore of the theory. They dictate how space-time curvature depends on the energy and momentum of matter. Or, as physicist John Archibald Wheeler beautifully summed it up, matter tells spacetime how to curve, and in return, that curved spacetime tells matter how to move. But here is the real kicker. This curvature, it's not just about physical space. The geometry of the universe dictates the flow of time itself. Because of the equivalence principle, if you have a clock higher up in a gravitational field and one sitting closer to a massive object, they are going to tick at different rates. This is called gravitational redshift. Time literally flows differently depending on your local space-time geometry. That is a wild, mind-bending mathematical claim, which naturally leaves us wondering, how on earth did physicists actually prove it? Section 3. The Proof, Classical Tests of the Theory. To verify these radical ideas, physicists had to use our entire solar system as a giant laboratory, and they found their proof in 3 famous classical tests. First, there's the anomalous precession of Mercury's perihelion. Mercury's orbit shifts slightly over time in a way that Newton's laws just flat out couldn't explain. But Einstein's curved spacetime, it predicted it perfectly. Second, they looked at the deflection of starlight, bending around massive objects like the sun. And third, the Shapiro time delay. This is where radar signals bounced off planets like Venus take slightly longer to return to Earth, simply because the signal has to navigate through the dents in spacetime created by the sun's mass. Let's zoom in on a very specific number related to that second test, 1.75. Einstein predicted that starlight grazing the edge of the sun would be deflected by exactly 1.75 arcseconds due to the curvature of space. The stakes here were incredibly high. I mean, if this measurement was wrong, Einstein's entire masterpiece would have collapsed. But during a famous 1919 solar eclipse expedition led by Arthur Eddington, astronomers measured the star positions and found they had shifted by exactly this amount. The real-world astronomical observations perfectly matched the theoretical math. So, since the theory held up flawlessly in our local solar system, scientists naturally started pushing it to its absolute mathematical limits. We wanted to know what happens when we scale up the mass. We wanted to see the extreme consequences of what happens when gravity becomes overwhelmingly, almost unfathomably strong. Section 4. The Extreme, black holes and the point of no return.
When you crank up the math to the absolute extreme, you discover regions where space-time just collapses in on itself. As you get closer to one of these incredibly dense, collapsing stars, the light cones, which represent all possible future paths a flash of light can take, physically tip inward. Gravity becomes so intense that it is pulling the very concept of the future toward the center of the mass.
And once those light cones tip far enough, you cross a threshold. You hit the event horizon. It's a one-way causal boundary in space-time. Energy, light, information, they can all check in, but absolutely nothing can escape to the exterior. The stellar matter inside is completely, utterly cut off from the outside world. An external observer can never, ever see what happens past this horizon. Now think about this for a second. If these incredibly massive, invisible, dense black holes exist out there, what happens when they move? Or better yet, what happens when two of them orbit each other and violently collide? A catastrophic event like that must leave some kind of dynamic, physical signature across the entire universe, right?
Section 5. The climax. Ripples in space-time.
When massive objects accelerate, they don't just curve space locally, they send out ripples of distortion at the speed of light. Imagine a perfectly circular ring of floating rocks out in deep space. As a gravitational wave passes through, it physically distorts that matter. The wave alternates between horizontal stretching while squeezing vertically, and then vertical stretching while squeezing horizontally. It's a literal, physical flexing of the distance between objects. To truly grasp how mind-blowing this is, consider the difference between this and what we're used to. Electromagnetic waves, like the light hitting your eyes right now, are phenomena that travel through space-time. But gravitational waves, they're ripples in the fabric of space-time itself. When we detect a gravitational wave, we aren't watching something move through space. We are literally observing the actual geometry of the universe vibrating. So, we've journeyed from a simple thought about a falling elevator through the intricate math of curving time all the way to the violent collisions of black holes sending ripples across the cosmos. Tying all these nested concepts together leaves us with one unified, awe-inspiring realization. The universe is bound by a single, magnificent geometric truth. The next time you drop an object and watch it fall, just remember that it is merely following the natural, curved pathways of reality itself. But it leaves us with one final, haunting question. If the very fabric of our universe can stretch, squeeze, and ripple like water, what other unseen geometries are waiting out there in the dark?